So maybe I will ask our first speaker, lecturer, to come on stage with me. Nikolai. Yes, there he is. I don't see your camera. Yes, there you are.
Yes.
Okay,
yeah.
so Nikolai, if you want to start sharing your presentation.
Yes, I will do
I will
it.
stop mine.
Just a moment. Just a moment. Just a moment.
And I see there's someone else on stage, but
yes, just
I will just.
Okay, it should work now.
Yes, we see your slides. So I will disappear now and we'll leave you the stage. Thank you.
Okay, yeah, thank you very much, Bruno, for your kind introduction. The title of my presentation is was already mentioned. In principle, we are partner in our European project REPTiS, and as Hereon, we have expertise in metal injection molding process, and especially we are contributing in characterization of the powder and mechanical testing and characterization of processed titanium components. Within the frame of our REPTiS project, we are considering two key additive technologies, namely metal injection molding, as it's here shown, and another technology is powder bed fusion with laser beam. They are schematically shown. But my talk will be in somehow general mechanical behavior of titanium alloys. We focus it on the most important titanium alloy, titanium 6-4. And I will talk about how we can understand and predict fatigue behavior of titanium components. If we consider, for example, additive manufacturing in principle in all processes, if we have parts, we will have or we will deal with surface imperfections such as geometrical defects and internal defects such as pores or other stress concentrations. In principle, we can try to optimize manufacturing technologies, but we will always dealing with some deviations. And the question is when the defects or stress concentration will be critical and how we can consider the stress concentration for predicting the fatigue behavior. Additional complexity in the case of additive manufacturing, of course, we have gradient of microstructure and also complex microstructures due to the complex heat treatment cycles. However, if we consider load-bearing components, nobody will apply the components with the surfaces as in as-built condition. We have to apply some technologies to reduce the stress concentrations from the surface. We can, for example, perform surface treatment or machining. And then internal defects will play a significant role. The internal defects will be also critical. For example, if we go to very high cycle fatigue behavior of the component. And our study is based on, for example, on the laser processes, because laser processes in principle can be also considered as additive manufacturing, important additive manufacturing technologies. And in principle, there are a number of similarities if we consider just laser beam welding or laser beam additive manufacturing. In principle, additive manufacturing can be regarded as a cumulative laser welding process where each subsequent layer is welded to the previous one. And here also subsurface porosity is a common reason for internal crack initiation if sufficient surface quality, grinding, machining, shot pinning, or laser pinning, laser remolding is applied. And subsurface residual stresses are present if we introduce shot pinning or laser pinning. And as laser beam welding is the most efficient technology to produce specimens with relevant microstructures for investigating the fatigue behavior, our study was focusing on the laser beam welded component at first. And then we are interested how we can transfer the results to additively manufactured structures. And here there are examples. For example, if we consider the fatigue behavior of laser welded or additively manufacturing components, also using laser beam, we see that we have similar behavior. If we have internal crack initiation from internal porosity, we have the so-called fish eye failure, and it is present in both cases, in laser beam welded joints or in additively manufactured structures. First of all, for general understanding, if we do laser beam welding, we have a number of challenges. We produce welding-induced defects, such as internal porosity, and we can have also geometrical defects, imperfections, or reinforcement. Another challenge is we have complex microstructure, and typically due to high cooling rates, we obtain a circular martensitic microstructure, and therefore we have low toughness, and titanium is well known as a material with a high notch sensitivity. We have even increased the notch sensitivity. And there are inevitable results of laser beam welding and also additive manufacturing processes. We can optimize, but we cannot completely eliminate the presence of defects. And the question is, if we consider the technologies for production of load-bearing components, we have to understand what is the mechanism of fatigue failure. We have to understand the effect of defects. We need reliable models for fatigue life prediction, and we need methods for fatigue life extension. If we are performing testing of titanium, for example, as a sheet material, we have that kind of fatigue results represented as a Euler curve. It means maximum stress of the cyclic loading versus a number of cyclic of loading cycles until failure. If we compare the behavior with the weld in a welded condition, you see we have a significant reduction in fatigue strength for both for finite fatigue life and for infinite for fatigue strength level. The first important reason is the presence of geometrical defects. The crack typically initiate from geometrical imperfection, fracture from the root underfill in the case. One possible way to improve the situation is, for example, to remove the geometrical defects, for example, using machining process, and then we are already in the improved condition. We are significantly higher with regard to as welded condition, but we still below the level of base material. And then here is already the situation for as welded. We have mostly incremental surface defects, but if we remove the surface defects, already the internal defects play a significant role, and therefore we have the level of fatigue strength below as it is in the case for wrought material. If we analyze the fracture mechanisms for the condition without geometrical defects, we see that here the internal defects play a significant role. We have fish eye crack initiation from internal porosity, and in this figure you can see clearly that we have, for example, several defects, and from two single pores, we have at the same time fatigue cracks which were initiated and go to the surface, but the pore in the middle was more critical one. And then if we look at the fracture surface in this observation at higher magnification, we see that we have a rough area in the around the pore. It's known as a optical dark area, and after that we have a smooth area where we have more plastic deformation during the fatigue crack growth. Therefore, the most important remarks are that the cracks nucleate at subsurface porosity. We have fish-eye pattern of fracture surface crack growth in a vacuum-like environment, because in the if we have crack initiation from internal pores, we do not have effect of the environment. And similar fracture type is well known for very high cycle fatigue for every kind of additive manufacturing, powder metallurgy, casting, and dwell fatigue. In order to understand how we can model the fatigue behavior in principle, we have to understand schematically what is our problem. The problem is we have internal porosity, and from internal porosity, we have the crack propagating to the surface. In principle, the assumption is that internal pore can be considered as a already existed crack, and this crack propagate to the surface if the crack meets the surface and the specimen or component fail. And in principle, we need to calculate the number of cycles required that the crack propagates in the fish-eye area. For every fatigue life prediction, one of the most powerful approaches is to do it based on fracture mechanics. If we consider the fracture mechanics-based approaches, in principle, we need to know the fatigue crack growth law, and if we know the fatigue crack growth law, we can integrate and calculate the number of cycles required to failure the component. In principle, the number of cycles from the initial crack length, it is our initial pore, and the cycles until failure if the crack grows to the surface. But here we have some challenges. We are dealing with very small cracks for the fracture mechanics. It means we need to know how the crack grows in the near the threshold behavior, and we need somehow input data with regard to pore size, pore depth, and material properties. First of all, with regard to fatigue crack growth model, here our assumption was, which was successfully implemented, is to use the so-called cyclic A-curve. Cyclic A-curve describes, in principle, the near threshold material behavior. It means we need to know the law, how the threshold of the material depends on the the stress intensity factor. And if we go to fracture mechanics-based approaches, there are a number of ways how to describe that kind of cyclic A-curve. For example, using this analytical equation where we need the data, for example, with regard to crack growth and the parameter A star, which we need. And if we have the crack in our component, we can use fracture mechanics-based approaches to calculate the stress intensity factor from the crack dependent on on its length. For example, this is the analytical approach. Delta K is equal to 2 divided through P, delta sigma, and square root of PA. It's our stress intensity factor. And the condition whether the crack will propagate or not is exactly there if the so-called crack driving force is our delta K has a tangential condition to this cyclic A-curve. The question is how we can identify our cyclic A-curve. For example, we can do fatigue tests up to 10 million cycles, and we can start with a cyclic stress level from the minimum value and step by step increase the level. If the component will not fail at 10 million cycles, we increase the level of cyclic loading and starting the fatigue testing again. And if the specimen fail, we assume that something in between is our fatigue strength. Then we can analyze fracture surface and identify the pore which was exactly responsible for the failure. And for this pore, we know the characteristics, the crack driving force, and considering the tangency condition to our A-curve, we can identify the parameter, the fitting parameter of our fatigue crack of our cyclic A-curve. Then we know our cyclic A-curve. Here is the picture is showing what we have in the case of a laser welded component. And you see that not failed component, if we analyze them, we are able to identify fatigue cracks growing from internal porosity, which were stopped at, for example, at grain boundaries. This is exactly the metallographic cross-section shows the case. And it is somehow the evidence and indication that the concept of fatigue strength is not meaning that we have our component without defects. It's the meaning that we have defects, but the defects, the possible fatigue cracks from these defects will be stopped. And the condition of fatigue strength is exactly the condition of crack arrest. So far, we are now know our threshold, near the threshold behavior of the material, and then we can include it, for example, in the NASGRO equation. And then we can calculate each point of the on the Euler curve by integrating the NASGRO equation. The question is, now we have the deterministic approach. The question is, if we are dealing with possible defects, we need to go to probabilistic approach. And how we can do it? For example, if we consider the distribution of defects, such as pores, with regard to their size, and, for example, the distance to the surface, pore depth. How we can do it? We can do, for example, to do it X-ray radiography. Here is an example of welded seam. And by analyzing the results of X-ray radiography, we can represent the distribution of pores with regard to their diameter and distance from the surface. And then we can mathematically describe the distribution. And now the color corresponds to our density distribution. And we can work with this approach. Here is our probabilistic modeling, the distribution of porosity with regard to probabilistic density function. And then we have already our model in principle for each point on this diagram with this axis, pore diameter and distance from the surface. We can calculate the fatigue life of the specimen. Below, in the region above, below where we have our delta K stress intensity factor near the threshold, it means that the pores are less critical, and the possible crack initiation from that kind of pores will result the crack arrest. And then in the right diagram, in principle, we have the situation that the color represents the fatigue life of our specimen. In principle, for example, if we consider this point with these characteristic values of the porosity, and each point from the diagram on the right side can be transferred to the diagram on the left side regarding the characteristic values of these pores. And you can see that the largest pore, it doesn't mean that the largest pore is a critical one. The criticality of the pore is a conquering situation between between this its size and position to the surface. And in principle, if we consider that all pores have to result to the number of cycles of at least 10 power multiplied by 10 power 5 cycles, we can remove or move this curve and consider that all pores have to be located under these curves. And this is in principle the area under this curve. It's the probability of failure, and probability of failure we can then easily calculate using this analysis. We validated this approach, and for example, using 16 specimens tested at different levels of cyclic loading, 525 and 550 megapascal. And here you see the points, the experimentally obtained results, continuous curves, blue one, and dashed curves, red one, are the results based on our model. You see we are in a very good agreement, and now we are able not only to predict the mean value of the fatigue behavior and fatigue strength, we can also predict the probabilistic stress number curves. And here is an example how we can do it for laser welded components. Now we can consider also the distribution of possible manufacturing defects in the prediction of the fatigue life of the load-bearing components. Okay, the question is how to transfer it to additively manufactured structures. We are still working on the processes considered in the REPTiS project. At the moment, I have only results for other additive manufacturing process, via arc additive manufacturing process, an example. And here we, in principle, investigated the approach in a similar way. We produced specimens that our other partner produced for us, the specimens using the via arc additive manufacturing process. And then we extracted from the manufactured block the specimens for investigating the fatigue behavior as SN behavior, and we extracted also the CT specimens to investigate the fatigue behavior with regard to fatigue crack growth, to identify the parameters of NASGRO equation to predict the fatigue behavior. And here are the results of predicting the fatigue behavior. In principle, here we have both situations. We have also fatigue cracks propagating from internal porosity. The number one marks the typical issue where we have cracks, but we have also another situation if the crack also located, or the manufacturing defects is located directly to the surface. Therefore, we have to extend our model also to consider the possible crack initiation from the surface. And we followed the same approach with a NASGRO equation where we identified the fatigue crack growth behavior and fitted the coefficients of the NASGRO equation. And here we also considered the two possible cases if the crack propagates from internal defects and for surface defects. Here is written how we can do it, and we identified also our cyclic curve. Here we used a little bit more modified equation describing the cyclic curve using the L-Haddad equation. And then, in principle, in the similar way, we can predict each point on Euler curve. Here are the surface initiation, and it is possible also to consider complex defects size, for example, using the Murakami approach. If we consider the area of the defects, then we can also consider the equal area with regard to the equal crack lengths for this area. And here are the results with regard to experimentally obtained results and predicted results using our model. You see, we are quite good with regard to twice error band or five-fold error band, but we have some specimens which showed lower fatigue life with regard to the predicted one, but we still are in the good level with regard to conservative fatigue life. But what could be the reason? The reason could be if we have a good agreement, we have defects with a round or more elliptical shape. But if we have defects with irregular shape, the deviation is probably due to the fact that how to consider what is the critical position of the defects with regard to the distance from the surface. And here we need somehow to further optimize our model. And that kind of approaches will be now investigated also within the REPTiS project for additively manufactured components. This was the one part of my approach, my presentation, and I would like also to mention some approaches how we can improve the geometrical, how we can eliminate the geometrical defects. I showed you that removing geometrical defects can be done using, for example, machining process, but another effective process is, for example, just to remelt using the defocused laser beam in order to obtain the more smooth surface. And with regard to fatigue behavior, this is somehow equal to the machining or cutting process. Another interesting process is what we are doing in our laboratory is laser shock cleaning process. The process schematically is shown here with a video sequence of the process. We're using high energy laser to introduce shock waves which can propagate through the material, and the shock waves can result deep plastic strains, and as a result we can introduce deep compressive residual stresses at lower surface roughness, and the process can be effectively used for retardation or suppression of fatigue crack initiation or deceleration of fatigue crack growth. And here is the demonstration how we can apply the process for specimens in as welded condition. We are able to introduce deep compressive residual stresses up to depths of 1 millimeter in the case of titanium 6-4 specimens. And as a result, we can also significantly improve the fatigue behavior by reducing the stress concentration at the surface. In principle, fatigue limit was increased by a factor of 2 by the LSP treatment. Now I would like to summarize my presentation. I showed you that internal defects are critical fatigue initiators, and the next important point was that fatigue growth from internal defects follows distinct mechanisms. Fracture mechanics based model can appropriately predict fatigue behavior not only for laser welded but also for additively manufactured structures. And unified modeling frameworks are transferable across manufacturing methods. Yeah, thank you very much for your attention.
Thank you, Nikolai. I hope you can hear me. Yes. Yeah, thank you for your presentation. We might have time for questions if there is someone. I don't see anything in the chat, but if anyone wants to pose the question directly, maybe it's possible. Otherwise, maybe I can start. I have one curiosity. I didn't know the laser shot peening, actually. I was used to the mechanical one. So the advantage is that you can also have effect inside, on not only on the surface. That's what I understand, correct?
Yes, important benefits of laser shock peening. We can create a significantly deeper effect with regard to introduction of residual stresses. And at the same time, laser shock peening in comparison to mechanical treatment techniques such as shot peening, for example, we have significantly lower effect with regard to work hardening. Therefore, residual stresses are more stable if we go to relaxation behavior or temperature effect. For example, fatigue behavior at elevated temperatures.
Yeah, there might be a question from Hamid. Hamid, do you want to switch on your microphone? Yes. And camera if you want. There you are. You can speak, yes.
You hear me?
Yes.
Yeah, thank you. Thank you, Nikolai, for the nice presentation. I have a question on one of the results of the fatigue testing you just presented, maybe on slide 1920.
Slides should be here.
Yeah.
Maybe I cannot hear well. What kind of what is the number of slide?
19 or 20, you said?
19 or 20.
No, maybe just before there was a stress level versus the number of cycles. Maybe the previous one. Yes, here exactly. As you have for the specimen that we had this WAAM defect at 6 times 10 to power 4. But for the specimens that survived at 10 to 7, do they have the similar size internal defects, or is just due to the lower level of stress amplitude that they were exposed to?
It is in principle. In principle, there are two exemplary of the specimens shown here. In principle, also in the region between 10 power 4 and 10 power 5, we have both situation, internal porosity, internal defects and surface defects. And in the region close to the fatigue strengths, we have also both situations.
Okay, so they're both. Because I was thinking if maybe you have investigated that they have like higher microstructural cleanliness, like fewer or smaller size of pores, but if it's
in the case of VAM, in principle, as we observed, we have significantly larger defects. It is in one case, for example, lack of fusion defect, and in another case, also some single pores were present, but in most cases, the challenge is if we have defects with irregular shape. This is a little bit more challenging to consider in our modeling framework.
Okay, and thank you very much.
Yeah, you're welcome.
Okay, if there are no other questions, I don't see anything in the chat, so maybe we can switch to the next lecture. Thanks again, Nikolai.
You're welcome.